Welcome. Let's learn Schmitt Trigger, the design and analysis. About the inventor, the circuit is named after its inventor, Otto Schmitt. Okay, and the original paper published was a thermionic trigger. So this Schmitt trigger, the original Schmitt trigger, uses a vacuum tube as the comparator. See, hysteresis is a important property of the Schmitt trigger. So let's see the etymology of it, right? So this word comes from the ancient Greek word hysteresis. Hysteresis means deficiency or lagging behind. So hysteria also means to come late, to occur late. So as a technical word, it was used in 81 to describe the behavior of the magnetic materials. Now, as a technical word, it's widely used in physics, engineering, and economics. So just to avoid confusion, there are two more similar you know looking words, hysteria and hysteria, but by root they have the different roots, not the same as hysteresis. Schmitt trigger is a special type of logic circuit that acts like a comparator with a twist. So compared to the regular standard logic circuit like inverters, right, uh, this Schmitt trigger has two threshold voltages, one for switching the output high and another for switching the output low. So this creates dead zone between the switching thresholds, making it immune to small voltage fluctuations and electrical noise. This hysteresis is the key feature of Schmitt trigger. It ensures the output remains stable even with jittery or noise inputs. These are the waveforms. See, we have op-amp based, IC based, and the transistor based Schmitt triggers. Our focus is CMOS based or MOSFET based Schmitt triggers. So let's look into the CMOS inverter and then move. So we have capacitances, gate capacitances. We have got on resistances of the MOSFETs. But important takeaway here is the switching, the characteristic of it. So it means whether my input of my inverter goes from 0 to high or high to low, the output always switches at the same point, VD by 2. Either this way also it switches at this point, or this way also it switches at this point. It means single threshold point, switching threshold. Let's see some applications. The very property hysteresis of this Schmitt trigger makes it usable in many applications. Some of them are noise filtering, waveform shaping or square wave shaping, oscillators design, and many more we can list. One notable thing I want to highlight here, for example, especially in IO circuits or GP, especially in GPIO circuits. So the Schmitt trigger is used at the receiver side of it. Signal coming from the external world are passed through this Schmitt trigger to filter out the noise. Right? This noise immunity is getting added to your IO circuit because of Schmitt trigger and because of hysteresis property of it. Okay, let's take two circuits. The left side is a inverter with a single threshold point. The right side is a Schmitt trigger with two threshold points. Okay, observe this. Threshold point means it's a input voltage for which output transitions. Okay, and this transition can be a different for high to low switching and low to high switching. These are threshold points. Okay, look at this diagram here. In the left side you see the glitches, in the right side don't see the glitches here. So it means any noise here is appeared at the output as a data or a glitch. Here look at it, this is appearing as some oscillations, glitches or wrong data. Here all of them are filtered out. This is all filtered out and we get a neat output. The same waveforms again I played them here. One key takeaway here is the hysteresis of the Schmitt trigger. How do you define it? Okay, how do you calculate it? So it's calculated by using this formula. So it's a difference of VSPH minus VSPL. It means difference in input voltages which are low switching points and high switching points. So here in this case, if we take it, so this is my VSPH. It means high switching point. This is my low switching point, VSPL. The difference, if you take it, this is my hysteresis of the Schmitt trigger. Then question is, how do we calculate in cadence simulator or in our simulation or verified, right? Generally what we do is we sweep DC sweep at the input, say 0 to VDD, and calculate this, check where my output is switching. That's my VSPH. Similarly, we sweep the input from high to low and check where output is transitioning, and I calculated this as a VSPL, and of course the difference is V hysteresis. Other than DC sweep, we always do transient simulations to make sure that functionality is all good. Yeah, right side is a symbol of the Schmitt trigger, left side is a transfer characteristics. Okay, how do you find out this? With DC sweep, input is swept from 0 to VDD, and the point at which the voltage at which output transitions from high to low is calculated. Observe, for typically assume that it's a CMOS inverter. So in inverters, like, so input is going from 0 to high. Okay, outputs transition from high to 0, some area, correct? And let's call it as VDD by 2, and maximum is VDD. Okay, so for this is an inverter switching point. Okay, it switches by VDD by 2. Even Schmitt trigger is nothing. I mean, in case we are talking about inverting type of a Schmitt trigger. Schmitt trigger ideally should switch here itself. Okay, input is rise from 0 to VDD, going up, output will switch from VDD. But because of the hysteresis property of the Schmitt trigger, it will not switch here. It is not switching at VDD by 2. It will switch little bit later. See the lagging bit, the word hysteresis, the meaning itself is lagging behind, come late, lag, deficient, right? So basically it's lagging. Instead of switching at VDD by 2, it is switching little bit later here and switching at VSPH. Hence the name hysteresis, the word. Okay, clear. Now let's take another example of it. Assume input is swept from 0 to VDD to VDD to say 0 volts, VSS volts. So input is falling, output should rise. It's an inverting type, right? So ideally expecting, I wanted it to jump at this level. Ideally I was expecting it to go up at this level at VDD by 2, ideally speaking. Okay, CMOS inverter does that work. Okay, whereas this Schmitt trigger will not switch at VDD by 2. It will switch little bit late. Input suppose switch here, it will little bit late here at VSPL. Okay, it switch up, output is switched up, again a lag, again a delay, then again a hysteresis property, right? Hence the property hysteresis. Let's understand this Schmitt trigger at steady state. It means we can classify into two parts. One is when VDD output is high and steady, when output is low and steady. Okay, logic high and logic low levels. Let's start with the first case. Output is low. Okay, it means this is at low, and naturally this has to be at VDD because this is inverting. This is basically an inverter, some modified inverter thing for all the reasons. Okay, so now what happens now? Okay, question. So now because input is VDD, M1 is on, M2 is on. Of course, this VGS and this VGS definitely bigger than VTH of it corresponding devices. And naturally, So this is at VDD, this is at VDD, right? So this VGS is 0, and naturally this also has to be something bigger than, lesser than VTH of it. So now of course this is again off. Clear? Okay, then let's look at what is happening to M3 and M6, this and this. Let's start with M3 first. See, this is at VSS, it means this VG is at VSS and this is at VSS. So this and this VSS minus VGS means VG minus VS, VSS minus VSS is a 0, it means lesser than VTH of it. So naturally this is off. Okay, off. And let's look at this point, right? So now look at it. What is the V gate? V gate is at VSS. What is this voltage? Is the question. Correct. So for all the reasons, think, okay, this is closer to the VDD. Okay, so it means source is closer to the VDD and gate is at VSS. Now VSG is closer to the VDD. Okay, and naturally it is on. This is the condition in the first case. Okay, let's look at the second case now. Let me clean it up. So now second condition is this one. Okay, when this is at VDD, and therefore naturally it has to be VSS because inverting Schmitt trigger, right? Okay, another simple inverter for all the reasons. Now what happens now? So now this VSG is VDD minus VSS is more than VTH on. Naturally this VSG, V source minus V gate, is definitely more than VTH of it, so it is also turned on. Now coming here, what is this VSG of it? VSS minus VSS. See, this is at VSS. So VGS of it is definitely VSS minus VSS is 0 volts only, right? So it is again bit lesser than VTH. It is off. Similarly, this VGS is also VSS minus VGS of this is definitely lesser than VTH. This is also off. Turned off. Okay, let's look into these two things now. Let's look at it first. Okay, so now see, this is at VDD gate and this is at VDD, closer to the VDD only. Okay, so VDD minus VDD, VSG is equal to V source minus V gate. It means this one, VSG is lesser than VTH. Of course we are talking about absolute of it. Okay, okay, so lesser than VTH, so it is off. Okay, so now look at this point now. So this is at VDD, VG is at VDD, and this is closer to the VSS, not exactly VSS, we'll talk about later. This is closer to the VSS, so VGS is definitely more than VTH of this device, so naturally it is turned on. These are the basic, the device, status, or the what region they are devices. Some of them are turned on, linear, some of them cut off. Yep. Now let's try to size our Schmitt trigger as per our switching points. Okay, and to begin with, let's assume the output is high. The output is high, 1. Input is 0. This is how let's assume with this condition. Okay, and for this region, because we use the lower portion. Okay, and I'm zooming here. Now since Vin is 0, look at it, this Vin is 0, right? This is 0 and M1 and M2 are off. This is off, this is off, because this VGS, VSS minus VSS, and this VGS definitely lesser than VTH of those devices and naturally off, because M1 and M2 are off. And Vout is, since Vout is high, right? This is high. This is high. Okay, this is 1. Since Vout is high, M3 is on. Why M3 is on is a question now. Look at it. To see this, I'm talking about the steady state, not just before steady state. This is at VDD, and this is what is this VGS of it? This minus this. Let me call this as a VX node. Okay, and this is at VDD, very clear. And what is this node VS? We don't know. Okay, so but to begin with, so this is at already at 0. Correct, but it's a weak pull up, it's off. Okay, assume it is at 0. Okay, and it's because it's VGS, this is VDD, this is VGS is VDD greater than VTH of it. This will turn on, M3 will turn on. Okay, and try to pull this device up to VDD. Okay, so after some time the Vx will settle at some other value, we'll see it later. Okay, now what is the source of M3? The source of M3 is now trying to, this M3 is trying to pull this source a Vx node to the up, right? But as we know that NMOS devices, they are a good conductor of zeros, but they are very bad conductor of, they don't conduct a very good, strong one. So what happens once this voltage, when it's trying to pull up to VDD, right? When it reaches VDD minus VTH of this device anyway, so this device will turn off because VGS becomes lesser than VTH of that device, right? So now what is that? This device is already turned off. This device turns off the moment it reaches this Vx reaches VDD minus VTH. We can call this as Vx floats. At what voltage? To VDD minus VTH of this device. VTH of 3. Just for an example, say assume VDD is 5 volts and VTH is 1 volt. This Vx floats at 5 minus 1 is equal to 4 volts. Okay, let me clean this. So when with V in less than VTH, it's clear, right? So Vx remains at VD minus VTH. As long as this M1 switches, okay, this Vx will remain at VD minus VTH because M3 is off, M1 is off, and Vx is floating at VD minus VTH because there's no discharge path or pull up or pull down path. So as we now, let's try to increase this V in. For example, we're moving this way. Okay. So as V in is further increased, M1 begins to turn on. This M1 begins to turn on because V in is VGS of it starts increasing. And the voltage Vx starts to fall towards VSS. This voltage starts to fall towards VSS because M1 is trying to pull it down. The high switching point VSPH, right? So the high switching point is this point, the point at which output is at VDD, it becomes 0. High switching point because it lies in the higher side of the input voltage, right? That's the reason. When for the input voltage for which output falls down, okay. So this switching point is defined when M2 turns on. Why M2 turns on? Because already M1 is already turned on. For output to down, only the obstacle now is M2. Anyway, M1 is already on, right? First M1 turns on, then M2 turns on. So that point at which M2 turns on, that's where we define the high switching point. Okay. Then let's understand the conditions of it. What are the conditions? See this. Let's analyze the VGS of it. Let's analyze the VGS of it. What is this VGS? This VGS should be greater than VGS2 should be greater than VTH2. Correct. So now what is V? That is equal to VG2 minus VS2. This voltage minus this voltage. That should be equal to greater than equal to VTH2. Okay. And then what is VG? VG2 is nothing but a V in voltage. So I'm replacing it V in. And what is Vs of it? It's nothing but a Vx node. I'm replacing it X node. So the V in minus Vx should be greater than or equal to VTH2 for the M2 to turn on. Okay, and now we define this imparity equation here. So it means for V in, okay, which I call it as a VSPH, the switching point, when V in is equal to Vx plus the threshold of this M2, that's where the output transitions from high to low, and I call this as a switching point. So now M2 starts turn on, output start to move towards. Since now both M2 and M1 are turned on, output starts to move towards VSS. Now what is happening as it is moving towards VSS, this Vx is strongly, further goes down. Okay, what making this VSS and making this also VSS, making these two VSS minus SS is equal to 0. It means VGS3 is lesser than VTH and it will turn off. This in turn causes Vx to go further, right? It's a positive loop, right? Positive feedback. So this is a repeated action, this goes down and this reduces. M3 loses control and this will conduct. Okay, so M2 turns on. This will continue till M3 is totally turned off and M2 and M1 are on. So the positive feedback causes the switching point voltage to be very well defined. This is a positive feedback, you can clearly see that. And now switching points are very well defined, we'll see it later. Now we understood at what point the output switches down, right? So let's try to size W and L's now. Okay, so see, with Vin lesser than VTH, with Vin lesser than VTH, so this Vx, right, remains at VDD minus VTH. We observed it. It floats, but it remains at VDD minus VTH for Vin lesser than VTH of this M1. The VSPH is defined, the switching point, right? VSPH is defined when this M2 is turned on, we said, correct? And what is the voltage we defined? That is Vx plus VTH of 2. So when this equation, till now we understood, right? Now when this equation is valid, it means at the edge of this M2 turn on period, right? At that exactly edge, okay, it's not yet turned on, but it's about to turn on. At that time, at that moment, we say this current is same. M3 and M1 current are same, correct? So drain IDS1 is equal to IDS3 because this is path exists here. Okay, this is turned on and this is turned on, but it's about to turn on, not yet turned on. So now we can equate the currents in the, what do you call that, equate the currents, and those equations are, beta by 2 into VSPH minus VTH and see VGS minus VTH whole square. Okay, so how do you say that, where beta is mu n COX WL, say of corresponding devices, think that way. And for IDS1, right, what this is VGS, what is VGS? VGS is nothing but V in, this V in, correct? Okay, so I'll read the VGS is equal to VSPH now, because I'm worried about the point at which it's turning on, right? VSPH. So VSPH minus VTHN1, that is equal to again VGS of it. What is VGS of M3? VG, this is VDD minus this Vx. Okay, so VDD minus Vx, of course, then minus VTHN of 3. It's very clear. Remember, so M1, it doesn't see any body effect, so I call this as a VTH naught only. Okay, however, look at these images. Let me clear this. However, look at this bulk is at VSS, this bulk is at VSS, whereas this is at again VSS, but see, this is already VSS. So now this and this M2 and M3, they see a body voltage, okay, backgate voltage, okay, voltage at the backgate. So M3 and M2 sees body effect. We call this as a backgate effect also. So naturally what? VTH of these M2 should be greater than VTH naught. How do you, what is the formula which defines it? Is this formula. See this equation. So it's very clear now. So this VTH is function of this body voltage, source to bulk voltage. Here this voltage, source to bulk or source to bulk voltage. So since here source to bulk voltage is bigger, I expect VTH to be bigger than VTH naught. Okay. So now let's consider M3 and M3 and M2. Okay, see M3 and M2, they share the same drain, which is Vx. Sorry, they share the same source, which is Vx. Okay, so their bulk is, of course, all the N devices bulk will be at VSS. So bulk is at VSS, both devices. Naturally, so bulk is at same voltage, source is at same voltage. Naturally, VSB is equal to VSB. Both of their both the devices V source to bulk are same. And naturally, because VSP is same, and VTH should be same for both the devices. So I can replace this VTH N2 with VTH N3. VTH N3. I can replace it. So that is the reason I can use here VTH N2 also. Now divide this equation. No, I mean just sort them in a proper order. So we beta 1 by beta 2. See this by this, let it come down this way. Okay. So beta 1 by beta 3, and which is of course which is equal to n what? So both are NMOS devices. This will get cancelled. So we can write it as W by L by WL. So W by L by WL. Okay, W. Okay, that is equal to, so this divided by this. Okay, so it means VDD. So I can replace this Vx plus VTH N2 with Vx plus VTH N2 with VSPH. I can replace it. I can put it here. Correct. So now it becomes VDD minus VSPH divided by, as it is, VSPH minus VTH N1. VTH N1, because I can put it as a, the without body bias in the VTH, not only I can put VTH N, I call it as. Okay. So this is your equation. Okay. Let's do some calculations now. Now it's very clear, right? So we derived it. So how do you size WL? By using this formula. Assume for a moment you have taken VSPH is equal to say 3 volts. Now for example 5 volt is a thing, right? 5 volt. It is supposed to switch at here, this point, 2.5. Let's assume it switches somewhere later. It means 3 volt, higher point. It might switch here also 2 volt. This is midpoint. Okay, this goes up. Let's see. I'm taking this 3 volts, assume the point, this point is 3 volt. Okay, this is supposed to be 2.5 midpoint, right, for a CMOS inverter, right? So now let's take VSPH is equal to 3 volts, okay, which is 0.5 volts above the midpoint. So now let's substitute them, the 5 minus 5 volt is the VDD minus 3 divided by VSPH is 3 minus VTH is 1. I'm taking 1 volt as a VTH. Okay. So now 5 minus 3 by 3 minus 1 is 2 by 2 is equal to 1. Then it's simple now. Say, of course, assuming L1 is taken as L2, all the generally in the logic circuit we try to take length minimum and we keep them same, right? So in that way, if we go with that logic, L1 gets cancelled. So in W3 is equal to W1 for this 3 volt of SPH. Let's do some other calculation also. Let's assume for a moment I will take this point as 3.5. Okay, so now 5 minus 3.5, this VDD minus VSPH, my 5 minus 3.5 divided by VSPH minus VTH of it, 3.5 minus 1 volt. Okay, that is equal to 1.5 divided by 2.5, it equals 3.36. In this case, so again assuming L1 cancels because we take the same length, so W3 is equal to W1 by 0.36. It means in this case W3 is bigger than W1. Okay, so now let's summarize this, the thing. Okay, generally for logic circuit we take length same and they are taken at minimum value. Okay, because we want to have a higher speed. Okay, minimum area and higher speed, higher current. So now I have to pick this W1, right? This W1. Okay, so then how do you start? We have to start with somewhere. Maybe you can start with the minimum. The way we do is start with inverter. Start with the minimum W. Maybe you can adjust late. So then what we now we got W1. We simply calculate W3. This device. How do you calculate W3? Is nothing but W1 by this ratio. This ratio. Now we got W3. What is remaining is M2. So M1 we got, M3 we got, we have to get M2 now. So now it's simple. The actual threshold is defined by M1 and M3 ratio, remember, right? So M2 is used as a switch. Okay, so and don't bother much here, just use W2, a thumb rule basically use it because it is a switch, thumb rule, use beta 2 greater than beta 1 or equal to. Okay, or sometimes if whichever is bigger, if B3 is bigger, use bigger than B3. Okay, so simple now. So now we are able to find out the W values of M1, M3 and M2 and for a given VSPH. Let's understand the other part, upper part. Okay, and size it for the other switching point, lower switching point. Okay, this original circuit Schmitt trigger. Let's begin our analysis of this circuit assuming output is at 0 and input is at high VDD. And as we know that these are the switching waveforms or transfer characteristics. So this time let's focus for VSPL. It means output is going up. It means at what input voltage output switches to high. That is a VSPL. Okay. So for this circuit we take a upper portion of this upper portion with zoomed here. Schmitt trigger is used. Now we know Vin is VDD, correct? This is at 1 voltage VDD. This is VDD, and of course this is VSS. Output is at VSS. So because this is at VDD, see what is VGS of it, VSG of it? VSG of it is 0. VDD minus VDD is 0, and of this also very closer to the 0. Very closer to the 0. Okay, we'll see it later what exactly. Okay, naturally M5 and M4 are turned off. Then Vout is low, correct? Because Vout is low, what is happening here? See, this VG is at VSS, and this, let's call this as VY here. This VY is closer to the VDD for a moment, think. So VSG is what? VSG is nothing but VDD minus VSS, which is more than VTH. So naturally it is turned on. Remember, now onwards, very clear, I'll not be repeating it. When I talk about VTH of PMOS, I'm taking absolute value of VTH. I don't mention it anywhere. I don't even talk about it's VTH means absolute of VTH of PMOS. Okay. So now VSD, V source to gate, is bigger than VTH of M6, right? Naturally it is turned on. Okay, the source of M6 now, to begin with, this is the condition, right? Then let's analyze what happens after some time, right? The source of M6 floats. Why source of M6 floats? To start with, it was on VSS, and this was at VDD to start with. Then it will start conducting. It was on. It start try to discharge this to the ground. Correct. And it start pulling this node down. Okay, because anyway this is off, it's not pulling up. Okay, this is pulling down, but we know PMOS doesn't conduct a good zero. It's a bad conductor of logic zero, right? Okay, so then it will pull it down only up to VTH value. After that it will turn off because VSG is lesser than or equal to lesser than VTH, right? It will turn it off. M6 will turn off by itself the moment VY touches VTH value of the M6. Okay, so now M6 is turned off, M5 is turned off, M4 is turned off. Of course, this VY node is floating. But what voltage? The voltage at that node is VTH of 6. It's very clear now, right? Now we understood this VY floats with voltage VTH of 6. Okay, just for example, assume the VTH of this M6 is a 1 volt, and the V5 floats at 1 volt. That's all. Okay, let's continue the journey with V in greater than VDD. VDD minus VTH. Now see this. What we are trying to do is we are reducing this voltage. This is VDD. And this is going towards VSS. Remember, similarly we are moving this input like this direction. It was at VDD, it's going towards 0. Okay, so now as long as Vin is greater than VDD minus VTH of this region, okay, M5 turns on. Yes, M5 keeps M5 is off, correct? Okay, so this voltage, because neither pull up nor pull down path is available, it floats at VSS at VTH value. As V is further reduced, for example, it goes down, V is further reduced. So now this VSG becomes greater than VTH. Okay, it will turn on. Okay, and because it's turned on, this node try to pull it up. M5 tries to pull this VY voltage to the VDD, start towards VDD. Now this device is turned on. So now my interested is at what input voltage this is output node is pulled up, right? Output node is pulled up this way, right? So this defined my now the point at which the voltage at which M4 turns on. Okay, so now I want to see at what input voltage M4 is turned on. Let's analyze that part now. Okay, so now what is VSG4? VSG4 should be greater than or equal to VTH4. Naturally, it means VS4 minus VS4 minus VG4. Okay, VS4 minus VG4. This should be greater than or equal to VTH4. So I'll write VS4 as V5. VS4 is V5. Okay, and VG4 is nothing but Vin. Vy minus Vg4 Vin. That should be equal to VTH4. From this equation, we get this important thing. So it means this Vin, now just rearranging the stuff, Vin is equal to Vy, this Vy minus VTH of 4. Vy minus VTHF4. V in is equal to Vy minus VTHF4. That we call it as VSPL. Okay, lower switching point. Okay, output is switching high, but input is at its lower part, lower of the two switching points, right? Like V in is equal to Vy minus VTHN4. Remember, some more exercise we'll do it later. So now, as M4 starts turn on, as V in further increases, V in further reduces, this VGS starts increasing further, and M4 turns on properly, and the output starts to move towards VDD. Okay, right, causing M6 to turn off. This M6 will turn off. Why M6 turn? Two ways you can look at it. One is this is going towards VDD. Otherwise, this is also going towards VDD. So now VDD minus VDD is almost towards 0. Okay, and it's lesser than VTH of this. Naturally, it will turn off. It moves towards turning off. This in turn causes Vy to go up further, right? Now this device is M6 is towards turning off. There is no pull down path here, right? Okay, so now this makes it further, okay, turning M4 even more. Okay, because this is going down and down, this is going up and up. Okay, M5 is only turning on, nobody is pulling it down, only M5 is pulling up. VS is pulling up, VG is pulling down, so VGS is keep increasing, and M4 gets turned on stronger and stronger. This continues till M6 is totally turned off. This M6 is totally turned off, and M5 and M4 are turned on. Now that we understood at what point the upper transition happens, okay, at what input voltage upper transition happens, let's try to size our the MOSFETs for a given switching point. Okay, the here means this transition. Okay, so now what is I'm interested is this is upper transition, right? Like output is switching up, right, for lower input voltage, right? There the two switching points in is lower switching, upper switching, high, sorry, not lower, high and low. Okay, so the output is switching high, and I'm interested in this voltage, and we know M4 is the one which is deciding the switching of this value, right? Okay, with V in greater than VDD, we understood already. With V in greater than VDD, okay, it means, yeah, VD minus VT by 5, Vy remains at VTP6. This Vy remains at VTP of 6, because after some time this is turned off. All of the upper side devices are turned off, and it remains at VTP6. And VSPL, the lower switch point, this point, right, is defined when M4 turns on. This is M4 turns on. Okay, and that is given by, okay, Vy minus, that is given by Vy minus VTHP4. Vy minus VTHP4. Since we already proved, okay, so that is equal to VTH of 4 is equal to VTH of 6. We can replace with Vy minus VTHP6. So body effect. When this equation is valid, M6 and M5 carry the same current. Okay, so M6 and M5 carry the same current, because this is turned off, is about to turn on, not eternally turned on, the edge you are talking about. So now this device is still on, remember, I mean trying to pull it down, and this is trying to pull it up, and this is at VTH of it. Okay, so this current is equal to this current, M5 is equal to M6, sorry, I5 is equal to I6. So the writing in the equations form, this is saturation equations, VGS beta by 2 into VGS minus VTH whole square. Okay, where beta is equal to mu p CY XWL, and we VTH this M5, see this bulk and source are at VDD, so it doesn't see any body effect. So that is equal to VTH naught of PMOS. Okay, so now I'm writing the equation. What is for I5, IDS 5 M5? So VGS is this much. What is VGS? What is this VGS? This much, right? Okay. Okay, right. So what is VGS? VGS is VDD. Sorry, VSG. I'm talking about VSG. VSG is VDD, and this is in my input. So my input is nothing but VSPL. Right. This is the one. Right. So VDD minus VSPL, that is VSG, minus of course VTH of it, P5. That is equal to, let's talk about the 6 now. Okay, again that is VSG comes into picture. What is this 6? VSG is this much, right? Okay. Okay. So VSG is what? V source is at VY. This is VY. V source is VY. And now we see that, right? Output is at ground. We that's what we assumed, and we are deriving these equations, right? This is at VSS. Right. So Vy minus VSS, that is VSG, minus VTHP of 6. VTH of 6. Okay. Now observe one important thing what's happening here. So we already discussed that with NMOS devices. So this bulk is at VSS. This bulk is at VSS. This bulk is at VSS. Remember, sorry, VDD. Sorry, this is VDD. This is VDD, and this is VDD. See, in this see source and drain are VDD. Remember, so I don't care. So VSB is bulk to source, source to bulk voltage is 0. VDD minus VDD. Whereas here, the source is not at VDD. This source. For this applies for M4 and M5X, right? So it means it sees a V bulk to source voltage. This also sees V bulk to source voltage. Okay, so bulk is anyway at VDD and source is not at VDD, so it means it's a bulk. Okay, so it means for those devices, the voltage is, the VTH is bigger, because look at this, bigger voltage. So VTH is bigger than, I'm talking about absolute. Okay, absolute value of VTH is bigger than VTH not. So for M4 and M6, we clearly see that just both sources are same. Bulk is at same VDD. Sources are shorted and at VI. So naturally, bulk to source voltage is same. VTH is equal to VTH. VTH4, right? So naturally, I'll replace 6 with 4. 4 and 6 are equal. I replaced with this. Okay. So I can use. So now, what is VSPL? We write this equation. Okay. Just rearranging a little bit here and there. Rearranging here and there. So now beta 5 by beta 6. Of course, if we get rid of this MPCOs which are common, I say WL by WL ratio here. WL by WL. That is equal to. So let's look at this VY. Okay, what is VSS is 0? I can ignore it. VY minus VTHP 6. VY minus VTHP 6. This one is came here. And let's look at this VDD minus VSPL minus VTHP 6. Correct. So now what is this? What is VY minus VTP 6? See, VY minus VTP 6, which is equal to VSPL, right? So I'll replace them here. VSPL divided by, as it is, keep it, VDD minus VSPL minus VTHP of VTHP. Okay, which is 5. These are my equations, final equations. Yeah. So what is my final equation is, this is important equation. Okay. So now let's calculate for, say, some one of the switching point, right? Last time what we did was I calculated for upper switching point, right? I calculated for 3 volt, right? I calculated for 3 volt. Okay, this is VSPH. Now let's do it for VSPL. The midpoint is say 2.5, right? Let me do it for 2 volt, 500 millivolt offset. Okay, so now VSPL is 2 volts, and that is equal to V divided by VDD minus VSPL 2 volts minus VTH. As I'm assuming VTH of PMOS is 1 volt. So that is equal to 2 by 2 is equal to 1. In this case, okay, this M5 and M6 have the same sizing. Okay, W6 is equal to W5. Is clear. Let's do it for some other values. So now let's do it other, maybe it switches here, assume for a moment, and we call this as 1.5 volt VSPL. Okay, so now for that 1.5 divided by 5 minus this one 1.5 0.36. In this case W6 is equal to W5 divided by 0.36. We learned how to calculate. If we know W5, we can calculate W6 for a given, switching point. Now let's summarize it. So how do we choose length? Now in typical logic circuits, we always pick minimum lengths for so many reasons. One is area, one is speed, and so many reasons. Okay, and generally we prefer to keep the same lengths in logic circuits. So we are able to figure it out length of the devices. Let's look for a 5 and 6. Always 5, generally we know it, right? How we size the PMOS, CMOS inverter, right? We take NMOS, lower NMOS. Depending on the ratio of the pull up and pull down strength, we size PMOS. Maybe 2 times, maybe 1 time. In lower technologies, it may be 1 time. In the olden days, it used to be 2 times or 2.5 times, right? So in that way, size W5, keeping W1 in mind. Okay, so is equal to ratio into beta 1. Now we know W5. W6 is simply the this ratio. Okay, is W5 by the ratio, whatever we got it based on your calculations. Now we understood, we calculated lengths, we calculated W, we calculated W6, W5, W6. Now what is remaining is M4. M4, right? So remember here, M4 is just used as a switch here, right? So M4 is used as a switch. The actual strengths are not decided by it. M5 and M6 fight for deciding the strength. Okay, that switching points. So M4 is used as a switch. Thumb rule here is use, choose W4 such that beta 4 is greater than or equal to beta 5. Sometimes beta 6, whichever is bigger, take that. Okay, so this is how we are able to find the W and L of all the 6 devices of the Schmitt triggers. I wanted to highlight some of the simulations here. The reason is we sized it, we designed it. Basically, paper design is that we have to verify it. How do you verify? By through simulations, either in cadence tools or whatever. So for finding out the switching points or switching thresholds, we generally go for DC simulation. We sweep the input voltage, DC sweep, see where output is switching. So that's 2 points. Once we sweep it from low to high, 0 to VDD, and other time we sweep it from VDD to 0, and see note down 2 different switching points. One thing, we also do transient simulations, because at the end of the day your transient simulations are working is good or not. Maybe you are shaping, converting a sine wave into square wave. In that way wave shaping is important, right? So the functionality is important. We do transient as well. Okay, I'm not talking about other simulations for power and everything. Let's stop here. Thank you for your interest.